All right, so now we want to apply our understanding of acceleration, our more in-depth understanding of acceleration, so that we can represent acceleration in lots of different ways. 5 different ways to be specific. So what we have here is an image that's referred to as Galileo's incline. We have a ball that's released along a long inclined plane, and you see the position of the ball every second for 5 seconds. And first of all, you notice that the spacing of the ball gets further and further apart, showing you that it's accelerating. Okay. Now, in this problem, I give you the first representation. I say it is found that the ball accelerates at a steady rate of, I should say, positive 2 meters per second per second. Okay. So it's accelerating. Well, if I know that it's accelerating at a steady rate of positive 2 meters per second, I can translate this into words. I can say the ball starts at rest. It says velocity equals 0 at the beginning. It's not moving. Every 1 second, the velocity changes by positive 2 meters per second. You could also say every 1 second the velocity changes by 2 meters per second in the positive direction, either way. So what that means is that if I say 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, if I want to know what this object is doing during those 5 seconds, well, if it starts at rest, 0, and it's changing by 2 meters per second every second, I go to 2 meters per second, 4 meters per second, 6 meters per second, 8, and 10. Okay? So it's another representation showing acceleration. Now, I know that I go from a velocity of 0 to 10 in, I go in a 5-second period. I'm going to go up to 10 meters per second. I'm going to start at the origin, and then I'm going to end at this point. And that would be what my velocity time graph looks like. Another representation. Remember, a diagonal line. Position time graph look like? Well, I'm going to start with no slope, kind of flat. And I'm going to end up at a steep slope, and so it's a curve. Something like that. Now for position time, I don't need to draw numbers here because we're not equipped yet with enough information. But these are 5 representations of acceleration for this Galileo's incline. You see how fast it would be going at 0, then 2, then 4, then 6, then 8, then 10 meters per second. You see that it means every 1 second the velocity changes by 2 meters per second. You see that that looks like a diagonal line on a velocity graph, and we can put numbers there. And you see that, hey, the position time graph would be a curve. So let's try one more. Poorly tuned car accelerates from rest to a velocity of 14 meters per second in 10 seconds. What's the average acceleration? Well, I can already come here and I can say, oh, well, it's starting from rest. It's going to make it up to 14. It's going to do that in 10 seconds. Well, I know it's going to look like that. Okay. My position time is going to be curve like it was before. Curve goes to a diagonal. And I know that I can calculate the average acceleration. I can say that, well, that's going to be a change of 14 meters per second divided by 10 seconds. So the acceleration is going to equal 1.4 meters per second. This means for every 1 second, or starting from rest, every 1 second, the velocity increases by 1.4 meters per second. Make that positive, okay? So that means that if I put in my values here, the time, and so on, that I'm going to be at 1.4 meters per second, 2.8 meters per second, 4.2 meters per second. And you see I filled out the rest. I paused and filled out the rest. So it goes up by 1.4 meters per second every second. And so I've now represented this motion 5 different ways. Velocity time graph, position time sketch, calculations, word statement, and data table.